Hello and welcome to another tutorial. So this time we are going to be continuing our exploration of data structures. And similar to the last time we were looking at the quadtree, we're again looking at another data structure for organizing spatial data. And in this case we're looking at that from a 3D point of view. So we're looking at what's called an octree. So there's a lot of different data structures we can use, but we're going to focus on the octree for this scenario. So let's dive on in. So this is in the same project as the quadtree one. And the very easy approach would be I could take the quadtree class and with very minimal modifications actually make that into an octree. I'm going to instead still build it up from scratch. The reason being is that if you just go and take the code, it can be very easy to make mistakes and miss things. It's also a case that I want this tutorial to kind of be able to stand on its own largely, so that if someone wants to dive in and look at how to build an octree, they don't need to go and look at the quadtree side of things first. So let's look at what we've got. We've got already set up in the scene a volume that it will spawn objects in. And if we run it, we'll see that it spawns currently 20,000 of these. So it spawns them randomly, so we've got a large number of them being spawned in there. We have this player that can move around, so there's a couple of little helper scripts, things like of that already set up. I've already created this obstacle script. So there's base versions of these already set up. They are there in a separate commit, so you can go to exactly the starting point for this. But the goal is as this player moves around, I want to find the objects in sort of a radius around me and then highlight them. So that's where the octree comes in, because rather than having to take all of the objects in the scene, all 20,000, and then find the particular ones, it allows me to go and actually grab a small subset of those and then use those for it. So let's take a look at the code. So one of the first bits of code that we've got is this obstacle 3D. And the two main files we're going to be working in are this one and our octree class itself. So I've set up this interface, iSpatial Data 3D. So the idea is that anything that is going to support being able to be stored in the octree must implement this interface. So I'm going to come over here and add in spatial data 3D, so it has to implement that. Now, in terms of what that interface does, what its purpose is, its goal is to give us all of the information we need to be able to store something in the octree. So there's a couple of key things we need. One of the things is we obviously need to know the location of what we're storing. So we're going to need a getLocation method. We need to get the bounds also for what we're storing. And there's kind of two aspects for how we want to be able to get the bounds. One is we want to be able to get just a direct bounding box. So for that, I'm going to have bounds, not bounding sphere, bounds, get bounds, like that. And then I also want to be able to get the radius of it, because that will be quite useful for us to have as well. So those are the three key functions that we need to have. Now, because I have set those up, that's going to mean that our obstacle 3D is now complaining, which is fine, because what we can do is we can tell it to implement all of these members. Now, at the moment, they're not doing what we need them to, which is fine. We don't need our diff. So what we can do is we want to now implement these methods. So, okay, I don't want to have to be generating this data all of the time, because if an object is stationary, then the information shouldn't change. So one of the things I'm going to do is I'm going to have it that we can cache the position. So we'll have, and you'll see what I'm doing here with this question mark, that's making this a nullable type. So normally, a vector3 being a struct, it wouldn't be able to be set to null, which means we don't have a good way of telling if it's not initialized. So by adding the question mark there, we make it a nullable type, which means I can tell that it's not been initialized. Then we have our bounds. That will also be a nullable type. And same with the radius. So, okay, that's good. We want to be able to tell if we need to actually update, so if our cache data has been invalidated. So I'm going to do this a little bit different to what I did with the quad tree. With the quad tree, I named this a has moved. With this, I'm going to make it a more generic, cache data invalidated. Is cached data invalid? And at a later point, I will actually switch the quad tree to using more this syntax because I think that's a bit more accurate. So, okay, if cached position is null, or if cached bounds is null, or if our cached position is null, then we'll return true, because the cache data is invalid, so we need to be recaching it. Otherwise, we know we've got valid entries for all of those, so we can check, has our location actually changed? Whoops, and that should actually be cached radius. So if that's the case, then what we do is it's invalid if, and we do a mathf approximately, so that will do a comparison with a bit of tolerance. So we do our transform position minus our cached position's value magnitude. So if that is not approximately 0, then we know our cache data is invalid. So what we can do here is these all get the exact same logic. So if is cache data invalid, update cache data. And then what we'll do is we would return cached position dot value, and it'll be pretty much identical logic for all of these. The only thing that will change is what we return. So this one will be the bounds. This one will be the radius. So nullable types, really, really handy. It's a really nice addition to C#. So we have our update cached data. Okay, so updating the cached position, pretty straightforward. Our cached position is transform position. Updating the bounds is also actually really easy because we have our linked collider and we can get its bounds. And then finally the radius is, we'll take our cached, well actually in this case, just to avoid the slightly slower lookup. So we get the extents and magnitude. So the radius here is actually more for, I guess, essentially a bounding sphere, which is completely fine. It just gives us something that's going to be reliably having a sphere that fits around it. So, okay, Obstacle 3D now has those necessary bits of information. It will cache data. It will update that data when it changes. So that's looking good. So now, all of the rest of the stuff we do is in this Octree. So it already has some interfaces here that we can see. It already has interfaces for being able to feed data into it, for being able to set it up, things like of that. And the structure of the Octree, much like the quad tree. So a quad tree, we have our parent node, and that splits into 4 children. With our Octree, we have our parent node, that then splits into 8 children. So 4 at the lower layer and 4 at the upper layer. Those children, much like with the quad tree, can also split, and if they split, they again split into 8 segments. So that's the general sort of structure that we have for it. And we store the data, typically in this case, we store it in the leaf node, so the lowest level nodes. So how we're going to work with this is we need to firstly be able to set up our nodes. So I'm going to have a class node, and then I'm going to define what these interfaces here should look like. So with things like these tree structures, stuff like of that, I like to write the code that uses them before I write the implementation of that code. I find it helps make sure that I'm getting the code doing what I actually need it to and not going off on sort of a bit of a divergent path. Very easy to have happen when you're working with something that takes a bit of time to implement. So always something to be mindful of. So add data and prepare tree. Well, prepare tree, I want to have here node, root node, like that. So prepare tree should be doing this, and it should be passing in our bounds, like that. When we add data to the tree, I want to be able to go, okay, well, root node, add data, and here's the bit of data to add. Our other add data function here, we don't need to do anything with. Stats we'll implement at the end. But in terms of our finding data in range, well, that's again going to be, we want a hash set. So I'm using hash sets because with the types of operations we're performing, a hash set is very, very well optimized for checking if something is contained within a set, and also for adding and removal. It works very efficiently for those. So you'll get much better performance than with something like of a list. So spatial data 3D, these are our found data. That's what we return. That's good. And then all we do is we would say root node and find data in range, and we give it our search location, search range, and the data like that. So, okay, I've defined how I want to be able to use this. Now we can start actually implementing it. And the vast, vast, vast majority of our logic actually sits within this node class. And generally, the node class is calling functions on itself. So most of it sits in here. So we're going to have our node bounds. So every node has a bounding box. We're going to have it being able to have children. And it's also kind of handy to store the depth for a node. That can be useful if you want to set a depth limit. It can also be useful just to get a sense of, okay, how deep is the structure that we're getting with the actual Octree. So you can just keep an eye on sort of that information. We need to store the actual data. So we have our spatial data 3D, like that. So, okay, well, first function we know we need is we know we need this ability to instantiate a node. So, okay, I'm going to have a public node. I have bounds, in bounds, and then we have our depth. which will give that a default of 0, so that then all we do is node bounds is equal to that, and we'll call that in-depth, just so it's actually consistent. So that's good. We've removed one of the errors. Now we've got only 2 errors left. They require quite a bit of code to make them work, but we do only have 2 errors left. And again, this approach allows us to, we know when we're done, when, in theory, when all of the errors are actually addressed. So, okay, adding data. Well, we know information-wise what we'll get in is this spatial data 3D. So we know that's what we get in. But what I'm also going to do, just because there's going to be settings we want to have in terms of minimum node sizes, stuff like of that. So it's handy to pass in the owning Octree. That allows us to store that data on the Octree, and if we change what information's there, it doesn't mean we need to go and change a whole bunch of function signatures, so it tends to work well. So, okay, if we are adding data to this, we've kind of got 2 main branches for this. One is if we've got children, and the other is if we don't. If we have children, then we want to store the data in whatever nodes those that data overlaps with. If we don't have children, then we need to just store it in ourselves. But we need to know when to actually split. So these are our sort of key branches. If children is null. So if that is null, then firstly we check, okay, is this the first bit of data for the node? Is this the first time we're adding data to this node? So if it is, so if data is null, then we'll just instantiate that so that it's all validly set up. Now we want to check, okay, have we reached a point where we need to split? So there's 2 criteria we generally want to check. One is a criteria for, yes, this is a good time to split, and the other is kind of a restraint, a restriction on that to ensure you're not splitting excessively. So what I'm going to do is I'm going to set up a couple of bits of exposed data here. So because these are going to be properties where I want them to be saved, I'm going to apply serialize field to the backing field of this property. This lets me set up a property where only particular things can, write to it. And in this case, only internal to the Octree can write to it. But external things can all read from it, but it's also saved. So it gives us a good balance there. So, okay, we have our preferred max data per node. And we'll do a get and a private set. I'm going to default that to 50. Now we do a similar thing. And this is where we set a size limit, where a node has to be of a minimum size to be able to split. Now the reason for that is we're using floating points for representing the bounds of a node. As floating points, they aren't a perfectly precise representation of a number. There is an error that creeps in there. So as our nodes shrink in size, we lose the ability to actually be able to meaningfully measure the size of those. They can get too small. And what can happen is the nodes can actually invert then. So we want to avoid that. So I'm actually going to have a minimum node size. Same thing. So that's good. So now I can check here, okay, am I actually able to split? So are we able to split? And this is a case of should we split and are we able to? So f our data count plus 1, so the new amount of data we would have, is greater than or equal to our owner's preferred max data per node, and we check if we can split, and we'll pass in the owner. So again, this is a function that we haven't implemented yet, but it's a fairly straightforward function. Have can split our owner like that. So if any of the dimensions are less than that minimum node size, then we can't actually split. So we return, what we can do is we can check our bounds dot, so node bounds dot size dot x has to be greater than or equal to minimum, or our owner's minimum node size, and our node bounds size y also has to be greater than that. And unsurprisingly, we then do the exact same thing with z. So if all of these criteria are met, then we are able to actually split. So again, we're going to set up what these functions look like. So we'll have split node, and we'll pass in the owner again. And then we want to take all of the data that we have got, and then we want to make sure that the data we're trying to add in here also gets added in. So we'll have a add data to children, and that will take in the owner and the datum. So if we shouldn't be trying to split, or we can't split, then all we do is data add datum. So fairly straightforward. And then with this, we can just do a return. And then here, we do our same add data to children, owner, and datum. So we've added in more errors, but that's okay, because we're going to be fixing those errors fairly soon as we implement those particular functions. Okay, so let's get these functions going, and we'll start with add data to children. So with that, its job is to take an individual piece of data and to then figure out which children that should be added to. So that data has bounds. If those bounds overlap with multiple children, then the data should be provided to each of them, so all of them get a copy of it. So we need to actually loop over all of our children. So child in children. And what we need to do is if that child, now we don't have this overlaps function yet, but we will. If it overlaps with the datum get bounds, then we'd say, okay, well, child, and we use our add data function from up here. So we tend to, the node communicates a lot within itself. There's a lot of the node calling its own functions. So, okay, we don't have overlaps. That's a pretty important one, so we'll get that going. So it takes in the bounds of something else, and all this needs to do is check, okay, node bounds, intersects with other. So that's good. We've got our overlaps, we've got our add data to children. We pretty much, our split node function is one of the big remaining ones. And it's one of the really important ones. And it's one that is very easy to have things go wrong with. So we're going to take the implementation of it slowly and carefully because it can very easily go wrong. But let's get this set up and we'll scroll this up higher. So we have our Octree and our owner, same as we do with the other ones. So firstly, it's going to split a node into 8 equal parts. So we want to work out the size of those first. So vector 3, child size, well, conveniently, if we use our node bounds, can actually just grab a copy of the extents because the extents are half the size. So really handy. Now, with how the bounds get positioned, we generally provide a size and a center location. So we need to be offsetting things. So what's going to make this easier is if I have just a general storage of our offset, and that is child size divided by 2. I'm going to store the new depth here just because we're doing the calculation in a lot of places, which while it would likely get optimized out, it's easy just to do this. It makes the rest of the code look simpler. So what I say is children is a new node. We have 8 children. And then I'm going to set up here, so we have new node, and I'm going to create, so we've got 8 entries here, and there is a reason why I'm doing this, and that is because this is where multi-line editing, actually, apart from just making it that we've got less typing to do, also actually makes it easier to avoid making mistakes and errors. So for initializing a node, we need to give it a bounds. Now the way bounds works is you give it a center location and a size. So everything is going to be some version of an offset from our node bounds center. And then the size, well, that's easy. That's child size. So that's creating the new bounds. Then we give it the new depth. And so all of our errors have gone, but we need to actually have the proper offsetting happening here. So we're going to add in a new vector 3. And this is going to be, and I'm going to put a little bit of a space here, offset.x, and an extra space, offset.y. The reason for the extra space we'll see in a moment, but it keeps things more lined up. So, okay. Now we can start to populate where these different ones should be, because we'll have an upper and a lower layer. So for the lower layer, we should be doing a subtraction, and for an upper layer, we should be doing an addition in terms of on the Y side. So the lower layer, we add in minus. So, okay, we've got 4 in an upper layer and 4 in a lower layer now. And now we can do the offsetting within those layers. So how we generally go about this is there should be a pattern to how these essentially are done. And so for X, if we do every second one, and then with Z, we do them in batches. So you should have all 8 possible combinations here. And this section here in particular, this offset, is the area where it can most easily go wrong. I often end up writing stuff out on paper. Multi-line editing has kind of saved the need for me doing that because it makes it a little bit easier to avoid issues. But this is, ironically, those 8 lines are the area where you're most likely to make a mistake with setting up an Octree. It's very, very easy for that to go wrong. So we've created the children. Now we need to distribute the data that we've already got to the children because the leaf nodes hold the data. And now that we have new leaf nodes on this, our data has to actually be redistributed. So we do an add data to children, and we provide owner and data, like that. So that will take all of the existing data and migrate that to the children, and then we can just clear out our data. So that's actually everything going for the construction of the Octree. So data should be going into that. And really, now all that's remaining is, and in this case we can provide that. All that's remaining is actually now getting this find data in range. We're pretty much at the, past the halfway point. So we're going to get our find data in range now going, because data will be going into the tree. Now we're going to be retrieving data from it. Okay, so let's get our retrieval of data from our tree happening. So we know that we want this ability to say, cool, give me all of the data that is in this particular range, and we give it a location, the radius, the distance from that, and we get out our found data. So that gives us our general structure. So I'm actually going to copy this so that we make sure it matches properly. So this will be a public function. Find data in range. So our search location is a vector3. Search range is a float. And our found data is a hash set of spatial data 3D. So, okay. Couple of things with this. Firstly, if this is being run on anything other than the root node, that's not valid. So if the depth is not equal to 0, then I want to throw a new, and we'll go for an invalid operation exception. Find data in range cannot be run on anything other than the root node. So I wouldn't normally do necessarily an exception for something like this, but this is a pretty critical error, so we should not allow it to actually continue. So, okay, I need to find the data in the range. So first thing I'm actually going to do is construct some bounds based upon our search data. So our bounds, so this is our search bounds. Here's a new bounds. Well, it's centered at search location, and I need to give it the size. So an easy way to do this is I can do search range times by vector3.1 times by 2, because the size is the full size of the bounds that we're searching within. So, okay, we've got our search bounds. So then I want to be able to actually retrieve data that sits within that. So we'll do the retrieval of it, and then we'll do a filtering afterwards. So, okay, I want to be able to go find data in box, and we provide our search bounds, and we have our found data, and I'm actually going to rename that to out found data. That. Then our find data in box is actually the main function we implement. So that, I think, is safe to be public as well. So we'll have find data in box, have bounds, we have our search bounds, and then we have our hash set again of the spatial data. And this is our outfound data. Okay, so if we have no children, then this is relatively easy. So children is null. Well, firstly, if data is null, or if we have no data, then we just return. There's actually nothing to do. Otherwise, well, the simplest thing to do is we do a union with the data. That's how we merge the data in, and we can do a return. So our box could be, overlap with the search bounds, and so some of the data we're adding in here could be outside of that, but that's okay because we can filter all of that at the end. So it's often with this cheaper to do more of the filtering at the end than to do all of it at the beginning. Then, okay, so that's if we didn't have children. If we did, then what we do, unsurprisingly, is firstly, we check if that child overlaps with the search bounds. If they do, then we go and say, well, child, find data in box, like that. So that's going to bring back all of the data in the particular box. So that should actually be enough for us to test this out. Now I'm going to reduce the amount that it spawns to 10,000. And I'm also going to make this transparent material a little bit more transparent. And I might make it just a pure white color. Makes it a little bit easier to see. So I'm going to select the player. And what we should see is a highlighted box there of everything. So it's not filtering by the range yet, but it is grabbing out the particular ones in that box. And as we move it around, see that, but it's doing a particular, like a node at a time, which is why we get these big, large jumps. But that's good. So firstly, what I could do is filter ones when we've actually done this sort of find data in box. So, okay, we could make an assumption that the root node will always have children, but that's not necessarily a good assumption that we should make. What we could do, though, is if depth is equal to 0, then we know it's the root node, we know there's no children, so that gives us a bit of an option here in terms of what we could do. So what we could do in this case is actually go through and check var datum in data if, and we can check, okay, our datum overlaps. We could say, so what we would check is if our search bounds intersects our datum's bounds, then we go outfound data and we add that in. So it's a bit of an optimized case for if the depth is 0. Otherwise, after we've gone and processed all the children here, if our depth is 0, then we can do a little bit of filtering. And what we could do is go outfound data, and we do a remove where, and the predicate we provide looks like this. set it up like that. So what we check is, okay, we return true, or returns true when it should remove it. So firstly, okay, it shouldn't remove it if search bounds intersects that. So if we do a not, that should now mean that we are filtering out ones that don't intersect. So let's make sure we comment this. If we're on the root node, filter out data not within search bounds. This is optimized check for a root node with no children. So just to make sure we're doing that proper filtering. Now what we should find with this is when we move the player, it's a little bit of a smoother transition. We see it's not jumping an entire node at a time. Now it's still not circular, or spherical in this case, and that's because we haven't done our final bit of filtering here. So what we again do is an outfound data, another remove where. We again provide our little predicate. So what we have, firstly, our test range, so the distance we're checking, is our search range plus our datum's radius. And then we return, well, if search location minus our datum get location. So what we can do is we can get the square magnitude of that, and if that is greater than our test range squared, we should remove it. So what we should find is that this gives us back a spherical shell of data. And if we move it up to the top, it'll probably be a little easier for us to see. It's one of the challenges with when it's 3D, is that it can be a little bit trickier to see that it is actually rounded, but we can see it is actually round, what we're getting back there. So that's good. But let's know how well this is performing. That's something we don't have data in here currently for. So let's start tracking that and reporting on that. Okay, so for tracking the performance, we don't want to be tracking the stats all of the time. So what I'm going to do is have a define here, Octree track stats, and this is very similar to what we did with the quad tree. So then what I can do is I can set up specific code only for being used in the scenario where we're actually tracking stats. So one of the key things that's useful to track is how many nodes we've got. So when we split a node, I'm going to check, okay, if this is defined, then I want to go and say owner, new nodes created, and I want to be able to be telling it I've created 8 and that the new depth is this. So it just gives us a little bit of info there. So that's the main thing within the actual nodes. Then when we're actually setting stuff up on the actual Octree itself, I want to have some bits of data that we actually store. So what I'm going to do down here is have hashf this. So we'll keep track of the max depth. We'll keep track of the number of nodes. Now we have our public void new nodes created, which gets our num added and the node depth. So that lets us update our number of nodes. And we update our max depth. These are just useful things to actually track and store. In our show stats, we do a similar thing of we have our define check, and we're just going to output max depth. Just useful little bits of data to be showing. And the reason being, we can spot things like, okay, has the tree not really actually built out to much of a depth, or has it built out to a point where we have a ridiculous number of nodes? It is a bit of a balancing act with these tree structures. More nodes means that there is more of them to churn through, so that has a performance hit, but it means the data within them is more likely to be entirely needed. So it's a bit of a balance there with performance. So that's good. When we prepare the tree, we should reset things. So max depth is 0, num nodes is 1. So that'll give us information about the actual tree itself. Now in terms of our search performance here, well, let's actually log out some stats. So what I'm going to do is I'm going to set up a stopwatch. The new system diagnostics stopwatch. So I start it, and then here I can go and turn it off. So we stop it, and then we log out exactly how much we found. So search found data.count results in, and then we indicate the time that it found it in. So our stopwatch and our elapsed milliseconds is a good one. So that should now mean that we get a little bit of debug data out, which is going to be useful. So we'll run it. So if we take a look at the console, it found 473 results in 3 milliseconds. As we drag it around, it's consistently taking about 2 to 3 milliseconds. Let's ramp up the amount of data here. So I'll go back up to 20,000. And then we can see how that's looking. So that is, understandably, going to be slower for performance because there's more data that it's churning through. But still, it's managing to process something that we've got, in this case, 4,000 nodes. So we could start to adjust things like, okay, what is the minimum node size? We could start to adjust things in terms of, okay, how much do we want to allow these to split? So I could allow 500 things per node. And we could see, okay, in that case, I've got significantly less nodes, but we'll notice the performance is actually poorer. So this is the balancing act with an Octree, is I could go to 250 and we could see with that. So adjusting, tweaking those sizes is a really important thing. We can see that's a little bit better, but 50 tends to work pretty well in terms of performance. You know, there are other things that we could do where, okay, for example, we're doing multiple rounds of filtering. I could turn off this filtering here when we are adding things. And with that, that might give us a bit of a performance improvement. but it does mean that that function is giving us back inaccurate data. And if we move the player, it's a little bit of an improvement, but not a huge amount of one. So we're sitting anywhere from 3 to 5 milliseconds. If I bring this back, again run it, here, that time it's 7 milliseconds. So it does give us a bit of an improvement. So one of the things we could do is we could give this find data in box. And we could have a precise bounds, or maybe exact bounds, which we default to true. And what we do is we only do this. So f exact bounds. And actually what I would do is depth is 0 and we're using exact bounds. Then we do that filtering. Same for here. So that way if we do want to exactly get that data, then we can. When what that allows us to do is this one can say, yep, don't use exact bounds. So now our one for searching within a bounding box can give us back precise data if we are wanting that, because there might be cases where we do need exactly that. But for things that make use of that, like the find in range, they can use the rougher data so that they're only doing the filtering once. So it's generally sitting a lot better now. So we have our Octree up and running. As I mentioned in the Quadtree video, there are further interfaces and things like that I want to add to this, things like raycasting, look at further ways of optimizing it and little things like that we can add to it to improve it. But we've got a functional one here, so dive on in and experiment with it. See what kinds of things you can do, see what kinds of mayhem you can create, test it out with different amounts of data. Main thing I would recommend is, in particular, if you're increasing the amount of data, make sure you save first. It's very easy to be spawning so many things that you entirely lock up your editor, so avoid losing work, make sure you save before running it. Thanks folks, hope you found the video interesting and helpful. If you have, chuck in a like and subscribe. It really helps out. It's really appreciated. If you had any questions or comments or other things you'd like to see me cover in videos, chuck those in a comment below. If you're looking for the code for the project, the code is available up on GitHub. There's a link to that in the description, and you can use the code in any of your own projects, commercial or non-commercial ones. You're able to be making use of it there. And if you're looking for other videos, there is a searchable video archive, also linked in the description. And finally, if you are looking for other ways to support the channel, then I do have a Patreon, and there's a link to that in the description also. But until next time,